Problem-solving examples, part 2. In this part, we do several more computation questions in our algorithms. All right, part F.1, 3 questions, number 11, number 12, number 13. All right, so number 11, it is known that a complete binary tree has n nodes. Which of the following numbers could be a possible value of n? Now, here, the given condition, complete binary tree. Here, when we talk about complete binary tree, so in your mind, you have a picture, right? Complete binary tree. All levels are for complete binary tree. Then, can you get an idea about the format of this node n? Right? Can you have that idea? Yeah. So the number of nodes, you just add up all the levels. The root level, let us assume level 0, okay? 2 to the 0. Then level 1, suppose the last one, level k minus 1. How about that? Hey, k minus 1. All right. So if you apply some formula, so add it up, you will get it equals 2 to the k minus 1. All right. So you can see a complete binary tree, the number of nodes take this format. All right. Now you check which of the 4 options has this format. That's simple. All right. Yeah. In other words, you can also do in this way. N plus 1 should be power of 2. All right, power of 2. Yeah. So in the 4 numbers, which one, if you add 1 on it, you will get power of 2? Which one? You just add 1 to it, to that number, you will get power of 2. Right? So that's simple. So this one, you add a 1, you get 512, which is 2 to the 9th. Yep. So you find the answer. All right. So it is just a simple property. Yeah. But you need to know it. Yeah. You need to know that property. Yeah. All right. Next question, number 12. This one. Yeah. This one, this time, I do not ask you to compare order of growth of these 2 functions. Remember, we did comparison a little bit before. Think about that, right? But this question, I changed the way a little bit. I want you to do the comparison for a specific number, n. Specific number. So then you need to do the calculation. Otherwise, you don't know which one is larger, which expression is larger. All right? So here, to do the calculation, so based on my experience, a large portion of the students do not know how to do the calculation. So here I want to show you. Here I just use the basic properties of logarithm and exponential functions to show you one example. So then later I will give you a similar question. All right, so let us plug in each expression and try to simplify it and see which one is larger. All right, the first one, A log base 10 of m. This time we write 10 to the 10 to the 106th power. All right. Looks pretty complicated, right? But can we treat the whole thing in the exponent as just one number? How about that? We treat the whole thing as just one number. In that way, whatever it is, base 10 here, log base 10 here, based on the property of logarithm, we have just the same as this exponent number, 10 to the 106th power. Yeah. So that's the first expression. After simplification, we have this. Next, the second expression. This time, n to the 0.0, how many digits after the decimal point? Six positions after the decimal point. All right. So let us simplify step by step. All right. So n, that number is, what is that number? 1 over 1 million, right? 1 million. All right. How about that? Yeah. 1 over 1 million. 6 positions, 6 zeros, right? Yeah. All right. 6 zeros. Yeah. Then let us write another, because we know this 1 over 1 million. Can we write it as 10 to the negative 6th power? Can we write that? Yes, we can. So this time, let us write 10 to the negative 6th power. All right, step by step. So then we can keep track of all the details, so we do not miss anything. Yeah. Now we are ready to plug in the concrete number for n. 10 to the negative 6th. How about that? How about that? Yeah. Then after that, we need to apply a property of the exponential function. The base 10 exponent, two numbers multiply together, 10 to the 106th times 10 to the negative 6th. How about that? Right? Yeah. So then further simplification, yeah. 10, yeah. Then 106 minus 6. How about that? How about that? Yeah. All right. Finally, we get 10 to the 100. How about that? Look at the exponent. Look at exponent. Now, when we compare these two numbers, let us just, because they have the same base, right? Both base 10, same base. So we only need to compare the exponent numbers. The first one, option A, exponent number 106, all right? B option, exponent number 10 to the 100th power. Clearly, B option is much, much greater than A option. How about that? All right, yeah. So now you can comfortably choose the correct answer. B is correct. All right, so that's the question number 12, the last question of this video. Yeah, this time we need to prove. Yeah. Expression, parenthesis, n plus 5 to the 4th. This function belongs to big theta of n to the 4th. Yeah. All right, So we show by the definition. Big theta, we know the meaning of big theta, right? Yeah. Big theta, by its definition, we need to find two constant, C1, C2. Okay, C1, C2. Yeah. So which side C1, which side C2? It's not important. Yeah. So need to find C1, C2, both positive, and 0 positive, greater or equal to 0. This is integer, all right, such that all right, lower bound, let's assume lower bound, C1 times n plus 5 to the 4th less than or equal to opposite. Because this function, growth function, is used as the reference. All right. So do not change the the row. The rows of these two functions different. Yeah. C1 less than or equal to n plus 5 to the 4th less than or equal to C2 times n to the 4th for n greater or equal to capital N0. That's by the definition, that's what we need to do. All right. But here, let me point out, many students, they tend to use a complicated way to solve. Yeah. Because I notice many students expand n plus 5 to the 4th, to many terms, right? Pretty long. Then from there, then do the estimate. Extremely complicated. Yeah. Although you can get it correct, but you need to do a lot of tedious work. So not very good. The efficiency is not very good. Yeah. Here, I just want to give you, when you see a question like this, try to use some simple way to do it. All right. Let us just look at this n plus 5 first. N plus 5 first, and find upper bound and lower bound. All right. Then from there, we raise all the expression to the 4th power. Then, much easier. All right? Yeah. All right. So, n plus 5, the lower bound size, multiple of n, that is just n. Okay? 1 times n. Yeah. So, for this is true when n greater or equal to 0, it is true. Because we only consider non-negative integers. For negative integer, we don't consider for our problem size, n, right? Here, n refers to our problem size, non-negative integers. All right. The other side, can we use 2n as the upper bound? But here, you need to specify n greater or equal to 5. How about that? Because when n greater or equal to 5, this 2n we know that is n plus n, right? Yeah. The first n equals that n. The second n greater or equal to 5. How about that? So you put them together, you get this simple version of lower bound, upper bound. All right. Then from here, next, when you move to 4th power, is it easy? Yeah, raising to the 4th power. So you get n to the 4th less than or equal to n plus 5 to the 4th less than or equal to the 4th. How about that? All right. So this you can simplify a little bit. 16 times n to the fourth. Then capital N0 for n greater or equal to 5. How about that? So this inequality is true for n greater or equal to 5. Then by the definition, we have conclusion belongs to big theta of n to the fourth. Yeah, that's by definition. Big theta definition, right? Yeah. So we complete the proof. So that's the recommended way to do the proof for a question like this. All right. Yeah. Then, before you leave, think about. Here, I use the plus sign. Can you think about if we do the similar question when use the negative sign to the fourth? How do we handle the negative number? All right. So think about it. Yeah. Using the similar idea. All right. So let me finish this F.1 right here.